So today we are going to discuss about Laplace transform. So generally Laplace transform of a function f of t is defined as it is denoted by L of f of t. Okay, it's equal to integral 0 to infinity f of t e power minus st dt. Okay, so this integral is the Laplace transform of function f of t. Okay, so this is the given function. So if we want to take the Laplace transform, we have to integrate the function with this weight factor. So with this I'll include some of the important properties which I have derived in another video, and you can look back to those videos if you want for the proof of some of the properties which I am going to mention now. So some of the properties, these are very important. So these are the properties of Laplace transform. Properties of Laplace transform. So these are some of the important properties. First one is the linearity property. Linearity property. Which says that Laplace transform of sum of two functions with coefficient a and b, if f2 of t, can be decomposed as a times Laplace transform of f1 of t plus b times Laplace transform of f2 of t. So this is the linearity property. And the second property is first shift property. The second one is first shift property, and it says that Laplace transform of f of at equals to 1 by a times f of s by a. Okay, here f of s by a is nothing but, so f of s is nothing but our integral. So f of the integral, we write it down here, the integral. So L of f of t, which is equal to integral 0 to infinity f of t e power minus st dt. So when we perform this integral, we have a function which is a function of s alone. Okay, so this f of s by a is nothing but this function where the s is replaced by s by a. Okay, so this is what the first shift property tells, that if Laplace transform of f of at, then it is equal to 1 by a times f of s by a. Okay, so thirdly we move on to the second shift property. Third one is second shift property, so which says that Laplace transform of e power minus at f of t, the product of these two functions, is nothing but f of s plus a. Okay, so if we have a minus a, then the function then the Laplace transform of e power minus at f of t is nothing but the function which results from integrating this integral, which is a function of s. We have to replace this s by s plus a. Okay, so similarly we can write L of e power at f of t equal to f of s minus a. Okay, so thirdly we have Fourier transform of a function which is a product of a function of t and unit step function. Okay, So the fourth one is Laplace transform of f of t u of t minus a. Okay, so this is the unit step function, and this is equal to e power minus sa L of f of t plus a. Okay, so just remember these properties. We can use it when we solve the problem. Okay, similarly we can write L of f of t minus a u of t minus a equal to e power minus sa L of f of t. Okay, so this is the Laplace transform which involves unit step function. And finally we have the Laplace transform of product of f of t and Dirac delta function t minus a delta of t minus a, and this is equal to f of a. Okay, the value of the function with this a. Okay. So with this property we also need some of the standard results, so we can use this property and standard results to solve the problems. Okay, so some of the standard properties, these are some of the standard properties. Let me write down some of the standard results of certain functions which we come across again and again. So these are the following standard Laplace transforms of some standard functions. Okay, so the next thing we are going to see is Laplace transform of some standard functions. Okay, so the first one is f of t. Okay, let me write it in this way: f of t Laplace transform of f of t. Okay, then this is equal to the function f of s. Okay, and this both are equal. Okay, so you can see that this Laplace transform is a function of s here. Okay, so the first function we take is the value 1. Okay, so if we take Laplace transform of 1, then we have our f of s as 1 by s. So you can see that the function, the Laplace value of the value 1 is nothing but the inverse of s. Okay, which is a function of s. So that's why we represent this Laplace transform, okay, as a function of s. Okay, so the next standard function is t power n. Okay, if f of t is t power n, then Laplace transform of t power n is equal to n factorial divided by s power n plus 1. Okay, so this is also equal to gamma of n plus 1 divided by s power n plus 1. Okay, both are equal. Sometimes we will use n factorial form, some other times we will use gamma of n plus 1 factorial, gamma of n plus 1 function. Okay, so the third function is e power at. Okay, so the Laplace transform of e power at. Okay, so this is the function we are taking now, and this is equal to 1 by s minus a. So again, the Laplace transform of e power at is L of e power minus at, and we can guess it's nothing but 1 by s plus a. Okay, the fifth one is the Laplace transform of sine at. Okay, so if our function is sine at, then L of sine at equal to a divided by s square plus a square. Okay, so the thing we have to remember is whenever we come across sign or sin h, then the numerator will be a. Okay, and if it is a trigonometric function, that is without h, then we have a plus here. Okay, so from this we can also write sin h of at. Okay, this is hyperbolic sign, so the Laplace transform of sin h at equal to, since this is sine, we have a in the numerator, and since this is an hyperbolic function, we have a negative sign, s square minus a square. Okay, so you can remember like this. So for cos, so if we look at cos at, so Laplace transform of cos at is equal to, whenever we have cos, we have s in the numerator divided by, since this is a trigonometric function, we have positive here. Okay, so s square plus a square. So the eighth one is cos h at. Okay, so Laplace transform of cos h at equal to, since this is a cos, we have a s in the numerator, and since it's an hyperbolic function, we have a negative here. Okay, so s square minus a square. So the ninth one is unit step function u of t minus a. Okay, so the Laplace transform of u of t minus a is equal to e power minus as divided by s. Okay, so the 10th one is delta function. If t of f of t is delta of t minus a, then the Laplace transform of delta of t minus a is equal to e power minus as. Okay, so in the properties we use f of the product of f of t and delta of t minus a. Here we use just find the Laplace transform of step function. So that's the difference. So we are going to use the properties mentioned earlier along with this standard Laplace results to solve the problems, and this is how we are going to solve the problems. So while mentioning about the properties, I forgot to include two more properties. So the another one is L of the product of function t power n f of t. Okay, whenever we have t power n f of t, then it's equal to minus 1 whole power n d power n divided by ds power n f of s. Okay, and similarly for division by 1 by t, that is L of 1 by t f of t equal to integral s to infinity f of s ds. Okay, so these are the two more properties we have to remember to solve the problems. Okay, so the one thing we have to remember here is this L of f of t, okay, is equal to this integral, okay, 0 to infinity f of t e power minus st dt. Okay, and this is equal to our function f of s. Okay, so if we evaluate this integral with these limits, we will end up with some function of s. Okay, so always remember this point. So sometimes it will be confusing how to find this f of s. Okay, so if we have to find this f of s using this integral. Okay, so let's start with the problem, with a simple problem. So example 1. So find the Laplace transform of L of e power at t power n. Okay, so we looking at this function, we can see that it is of the form in the second shift. It can be solved using second shift property. Okay, so it says that whenever we have e power at f of t, we have to find so in our case we have to find f of s first, which is nothing but the integral 0 to we can find it through the Laplace transform. So it is nothing but L of f of t. Okay, here we have to take f of t as t power n. Okay, this is our f of t now. Okay, so if we take that, then we have the second shift property form, which is e power at f of t. Okay, and this we know that it's nothing but f of s minus e. Okay, so we have to first find f of s, and in that function we have to replace s by s minus a. Okay, so let's do it. So in our case our f of t is t power n, so this becomes L of t power n. Okay, so we know that from our standard results, this L of t power n is nothing but n factorial divided by s power n plus 1. So we have a function of s. Okay, this is our f of s. So our L of e power at t power n is nothing but, so this is our f of s. We have to replace the s by s minus a if we have e power at. Okay, so we can write this as n factorial divided by, since we have s here, we have to replace it by s minus a whole power n plus 1. Okay, so this is the Laplace transform of e power at t power n. Okay, similarly we can find the Laplace transform of example 2, e power at minus at t power n. Okay, and this is nothing but f of if we have f of t, then it is nothing but f of s plus a, and in our case in the place of f of t we have t power n. So we have to find first f of s, which is nothing but L of f of t, which is equal to L of t power n, and it's equal to n factorial divided by s power n plus 1, and we have now this is s. Okay, so we have our f of s. Then for this first shift theorem, by using first shift theorem, we can write L of e power minus at t power n as n factorial divided by, instead of s we have to put s plus a, since we have a minus here. Okay, so it is nothing but f of s plus a whole power n plus 1. Okay, so next we can see example 3. So we have to find L of e power at sin bt. Okay, so for that we have to take this as our f of t. So then we have to first find f of s. So f of s is nothing but L of f of t, which in our case L of sin bt, which is equal to, since it's a sine, we have a in the numerator, and since it's a trigonometric function, since we have no h here, we have to use plus here. Okay, s square plus a square. So this is our function of s, and since we have e power at, we have to replace s by s minus a. Okay, since we have plus here, so our f of s plus minus a. Okay, s minus a is a divided by s minus a the whole square plus a square. Okay, so L of e power a t sine, so sorry, since we have b here, we have to put b. Okay, b square, we have b square here. B. Okay, so this is what comes here in the form. So bt equals to b divided by s minus a square plus b square. Okay, and this a comes from this a. Okay, and this b comes from this b. Okay, so let's do another example, similar example. Example 4, let's to find L of e power a t sin h bt. Now we have an hyperbolic sign, so this is our f of t now. So first we have to find f of s using this f of t. So we have L of f of t, this is L of sin h bt, which is equal to, since it's a sine, we have our b in the numerator, and since it's an hyperbolic, we have a negative, so s square minus b square. So secondly, we have to find our f of s. Since we have a plus a here, we have to find f of s minus a. Okay, so we have to replace s divided s by s minus a. Therefore we have b divided by s minus a the whole square minus b square. So L of e power a t sin h bt is equal to b divided by s minus a the whole square minus b square.